Welcome to day 2 of Biostatistics 3. On day 2, we will review hazards and rates. We'll have a discussion on different timescales. We'll talk about modeling rates using Poisson regression. We'll talk about adjustment for confounders, interactions, and re-parameterization for different contrasts. And then we'll also talk about confounding by time. We've already defined that the survival function S of t is the probability that some random time variable t is greater than small t, which is equal to 1 minus the the cumulative distribution function, or the failure proportion. And we've also already defined the hazard function as the limit as delta t becomes smaller and smaller of the risk of having the event between t and delta t as an instantaneous risk, but conditional on not having the event prior to t. The hazard function shows how the hazard rate varies over time, and it can be considered the instantaneous event rate at time t, conditional, importantly, conditional on survival up to time t. From equation 2, we can see that lambda t times delta t may be viewed as the approximate probability of an event who was alive at time t experiencing the event in the next small time interval delta t. The events so the units for this are in the number of events per unit time. Note that the hazard is a rate, not a probability, so you can take any value between 0 and infinity, while the survival proportion is restricted between 0 and 1. And if you get a lower value for the hazard, then you get a higher value for survival. If you get a higher value for the hazard, then you get a lower value for survival. There is a close relationship between the hazard function and survival. First, let the hazard lambda be constant. Then survival S of t between time 0 and time t is approximately 1 minus lambda t. We can improve on this calculation by breaking the interval between 0 and t into n segments and calculate the probability of surviving each of the segments. And then letting n become large, we have that survival is equal to the limit as n gets larger and larger and larger of the product of the survival for each of the time segments. And each of those time segments is equal to 1 minus lambda t over n. And then as this becomes larger and larger, this becomes smaller and smaller, and then 1 minus this value is approximately equal to exponential of minus lambda, minus this value here. So then we have, we can use the exponential, and then once we've got the exponentials, we can put the product inside, and it becomes a sum, and then this just reduces down to this value here. And this is the survival function for an exponential distribution. More generally, the hazard may vary with respect to time. So this sort of shows that we have lambda at t divided by n as we're moving across the different segments. So again, what we have is survival is equal to the limit as this value gets large of the product of these conditional probabilities. And then again, what we do is this value here gets smaller and smaller and closer to 0, which means that we can use the exponential of that. Then what we can do is say that as long as the lambda is well behaved, we can take the product inside, and we can also take the limit inside. So then we have an exponential of a minus limit of the sum here. Now, this value here can be interpreted as the area under the curve for the lambda function, which is just the integral. So we have exponential of the minus cumulative hazard. As noted earlier, the hazard function can be calculated as the negative change in log survival, and it can also be calculated as the rate of decline in survival. So it's the slope in survival divided by survival, the negative sign because it's always decreasing, and these we can calculate lambda from both of these values. It can also be shown that this value here is also equal to the cumulative hazard. So some statisticians will explain that the hazard is technically the instantaneous rate. So that means the rate r s of t between times s and t, which we know as being the expected counts and the expected person time, is that value here can actually be calculated by, you've got the survival and the hazard divided by the person time here. So what this shows is that as S and T get closer and closer together, then the instantaneous rate here gets closer and closer to the hazard. If S and T are wider apart, then the rate becomes a weighted sum of the hazards. Choice of timescales. There are several timescales along which the rates may vary, and these differ from one another, but in the choice of time origin, so the point at which time is 0. So consider the following questions. What is the time? How old are you? And how long have you lived in your current address? What is the time origin for each of these? And in which units would you specify in time? And could different units have been used? I'll give you a chance to reflect on this. So, what is the time? So it's actually normally this is this is time from midnight how old are you? This is actually and that would generally be measured in hours or minutes. How old are you? The time origin is your date of birth, and that's usually measured in years, but it could be measured in months or days for infants. And how long have you lived at the time origin? So that would be from the date of move to the current address, and that could be measured in minutes, hours, days, years, or even decades. So the time progresses in the same manner for all three of these. But we could use the different time origins or use different units. To give an example, based on our 35 patients with colon carcinoma, what we have is we've got an individual here who started around here and is followed and then has an event. So this was actually that they sort of started maybe late 1993 and had an event close to beginning of 94. Now that same individual could have been sort of like moved and sort of said that they sort of they entered at time 0 for study entry, and then they're followed for a short amount of time. Notice that the person time for this individual does not change. The event indicator does not change. The time origin does. So what we have here is you've got an individual who entered close to the late, but probably in 1989. Then they were followed through to the end of 1996, and then they were censored. The same person time can be represented on another time scale. They entered at time 0, and then they were followed for just over six years. So the same individual, we could also look at their age at study entry and their age at diagnosis, and then these data would have been spread out much more. Common timescales. If the timescale is age, then the time origin is birth. The timescale is calendar time, then we just choose a fixed date. Time exposed, then the origin will be the time that they are first exposed. Time on study would be entry into study. Time since onset would be the date of the disease onset. Time since diagnosis would be the date of diagnosis. And the time on treatment would be the date that they started the treatment. In many of the methods used in survival analysis, effects are adjusted for the underlying timescale, and therefore the choice of timescale is extremely important. On many timescales, subjects do not necessarily enter follow-up at the time origin t equals 0. So t naught could be quite different from 0. To deal with those issues, the serve function allows for both entry and exit times to be specified prior to the event indicator. Right, returning to thinking about censoring and truncation. To review with right censoring, which is the most common form of censoring in medical studies, we know that the event has not occurred during follow-up, but we are unable to follow up the patient further. We know only that the true survival time of the patient is greater than the given time. We could also have left censoring, where we know that the event has occurred prior to the time of observation, but we don't know exactly when. Interval censoring occurs when the event has occurred between two time points, but we don't know the exact date. And indeed, an example here could be that an HIV infection is between two test dates, or that they got cancer between two screens. Standard methods for survival analysis assume that all censored data are most standard methods assume that they're right censored, which we will tend to assume in this course. Left censored data and interval censored data will require special methods. So, as we've already discussed, censoring refers to the situation where we can identify the individuals in our study, but we don't have precise information on the event times for all individuals. A second feature of soil studies, which is often confused with censoring, is truncation. So truncation refers to the situation where certain subjects are screened such that the investigator is not aware of their existence. Left truncated data occur when we only observe the individual if they are event-free after a certain follow-up time. For example, late entry to study or using age as the primary timescale. The distribution is conditional on entry at the left truncated time. So what we essentially do is we sort of say the distribution for those individuals is conditional. It's basically truncated. You drop the first part of the distribution and you only get the second part. Left truncation will change who is in the risk set at different times, and will also affect the person time observed. Methods for left truncated data are available for hazard estimation, Poisson regression, Cox regression, and generalized survival models. Right truncated data occur when only individuals who experience the event of interest are included in the study, and special methods are required for their analysis. As a graphical representation, well, what we could have is we've got the exact time. So this is an individual who had the event at 5 years. This is that an individual, if it's right censored, for this individual, they did not have the event at 5 years. Left censored, they had the event between 0 and 5 years. Interval censored, they had the event between 4 and 6 years. Left truncated with exact times. What we have here is a conditional distribution. This individual entered the study at 2 years, and then they had an exact time at 5 years. Now, notice that this distribution here is not exactly the same as this distribution here, where the left truncated distribution is scaled up. And we could also have the same thing where you could have that they're left truncated and right censored. So they entered at 2 years, and then at 5 years they were censored, and they did not have the event. So again, this is very similar to this, except that the probability density function is scaled up, because we essentially ignore this area and we ignore this area. To make it possible to do a straightforward analyses, we often make the assumption that conditional on the values of any explanatory variables, censoring is unrelated to prognosis. So those methods assume that the prognosis for an individual censored at time t will be no different for those individuals who were alive at t, but and were under follow-up past t. So one way to think about this is that conditional on the values of the explanatory variables, the individual censored at time t should be a random sample of the individuals at risk at time t. This is known as non-informative censoring. Under this assumption, there is no need to further to distinguish between the different reasons for right censoring. However, when withdrawal from follow-up is associated with prognosis, this is known as informative censoring, and standard methods of analysis will result in biased estimates. Common methods for controlling for informative censoring are stratification and conditioning on those explanatory variables on which censoring depends. Thankfully, censoring due to termination of the study or accidental death are usually uninformative, which makes our life simpler, but careful consideration should be given to other forms of censoring. And from a philosophical perspective, determining whether or not censoring is informative is not a statistical issue. It must be based on subject matter knowledge, so you should think about it carefully. Returning to the diet data, what we have is we have a variable DOE, which is the date of entry. We have DOX, which is the date of exit, and we have an event indicator CHD. So what we do in our code is we can specify time as being serve t-stop, I think we're going to have t-stop is going to be equal to dox minus doe. So what we have is that the time that they're followed and the event indicator means that you've got right sensor data, but if you have a t-start and a t-stop and an event indicator, then this shows that it's left truncated and right censored. This is when they enter, this is when they exit, and this is what the event is. So to sort of take this example further, if we assume that there's approximately 365 and a quarter days in an average year, what we can do is we can take with the diet data, we can look at serve for DOX minus DOE. This changes it from dates to years with CHD as the event indicator. And what we have is that the first individual was followed for almost 16.8 years, and they were censored. The next individual was followed for almost 20 years, and they were also censored. And then the 1, 2, 3, 4th, the 5th individual was followed for almost 1.5 years, and they are an event. So each individual enters or becomes at risk at follow-up time 0 in these examples, because DOE is the calendar time of origin. When we divide by 365, we go from days to years. The event is coronary heart disease. Now, if we were instead to be looking at attained age, what we can do is date of entry minus date of birth divided by scale. That gives us the age in years. Date of exit minus the date of birth divided by the scale. That gives us the date of exit. So the first individual was followed from 49.4 years through to 66.2 years, and they were censored. The next individual was followed from 47.5 years through to 67.5 years, and they were censored. To use calendar time as the time scale, then we could have year of entry, year of exit, and CHD. So then you'd have left truncated data, possibly right censored. It could, we could also define the time origin as the 1st of January 1990, which is an arbitrary fixed year. So what we have is time origin is as date 1900-0101, and then we do the date of entry minus this time origin and express the values in years. Date of exit minus this time origin, express the value in years. So the first individual entered in 1960, just at the beginning of 1960, and was followed through to almost the end of 1976, and they were censored. Then the next individual was entered the study in towards the end of 1956. They were followed through to almost the end of 1976, and they were also censored. Right, from a non-parametric estimator of survival, we can calculate the steps in the cumulative hazard function. And then what we can do is we can smooth those steps to estimate the hazard function, much like what we would do for standard density estimation. However, the challenges that we have for density estimation are the same for doing hazard smoothing, that we have to when we do the smoothing, we have to choose the bandwidth or the amount of data to use when we calculate the smoother. Because of this choice, my advice to you is do not overinterpret the estimated smooth hazard functions. The smooth hazard functions give you a nice idea so far as the broad shape, but don't over interpret the shape. So the Biostat 3 package provides a server interface to the mu has function from the mu has package, and for right censored data. For right censored and possibly left truncated data, you can also use the BS hazard from the BS hazard package, and we'll show examples of this. So what we do is, if we're looking at time since calendar entry as the time scale, then what we do is we plot a BS hazard object for soil time, which is, this is time since entry in years for CHD. For the data, then we change the y-axis limits here and here, change the labels here and here. Then I think the default is to include the confidence intervals for the BS hazard when we do this plot. Then we also use the mu_has_2 function for the same survival data. And then this just sort of says change the line type to doing dots and make it slightly wider. So these are the dots here. And then what we do is we can add a legend in the bottom left. Don't put a box around it for line types 1, 2, and 3. Colors black for the BS hazard, gray for the confidence interval, and then black dashed for the mu hazard. So, and this shows essentially that there's fairly strong indication that the hazard does not change substantially between 0 and 20 years when we use time since entry as the timescale. If instead we do this for CHD with attained age, so date of entry minus the date of birth expressed in years, date of exit minus the date of birth expressed in years, changing the y limit again to have those two values, and changing the X label. Then we find a very nice association between attained age and CHD, and that is actually not that surprising based on our understanding of the disease, where the disease incidence increases with increasing age. So this would be a strong indication that we would prefer attained age as the timescale over time and study. If we were to look at calendar time, so then what we do is we have the this year function, which I think is defined in the Biostat 3 package, which takes the date and produces this as a continuous year, date of entry, date of exit, and CHD as the event indicator. Again, we're using the same y limits, and then we have calendar time here. And again, we find no strong association. So to review, what we found was no strong association with time since a study entry, no strong association with calendar time, but a very strong association with attained age. Okay, so I'm now going to take you through a bit of a digression to do with R. I'm talking about formulas and factors, and I think this is important for understanding how R constructs the design matrices from formulas for factors. So what we do is let the linear predictor for the right-hand side of a formula be represented by eta, where eta is equal to some design matrix and a bunch of parameters. And this will come. This should become obvious from the examples. And what we do is we use some example data where we have high energy, which takes factors which is low and high, and job, which takes factors driver, conductor, and bank workers, and then just a continuous value x, which goes from 1 to 6. So we have these three variables. So the first row of this data frame is low driver 1. The second is low conductor 2, low bank 3, high driver 4, high conductor 5, high bank 6. And now if we do a model matrix from the formula tilde x from this data frame, what we do is we get an intercept term and a continuous term, and the linear predictor eta is equal to beta naught for the intercept term and beta 1 times x for these values here. Then what we can do is we can change the formula to being tilde x minus 1, and what that does is it essentially drops out the intercept term, and so we have eta is equal to beta 1 times x. Then what we do, if we have a two-level factor, such as high energy, I should go back. What this assumes is that low is the first value and driver is the first value. And then what we do is it treats low and driver as being the reference variables. So then what this does is it still defaults to giving us an intercept term and then compares the reference with high. So then for the first three groups, they were all low energy. So this these values are 0, and then they were all high energy for the rows 4 to 6. We can express the linear predictor as an intercept term from here plus beta 1 times I, and this is an indicator term which takes values 1 when this is true and 0 when this is false. So this is eta is equal to beta naught plus beta 1 times I high eng equals high. Then what we can do is if we remove the intercept term, strangely enough, it doesn't drop this term at all. What it does is it instead says give us an intercept for those which are low energy and intercept for those that is high energy. So the linear predictor is equal to beta 1 times I high energy equals low plus beta 2 times I high energy equals high. Now this broad pattern here, if we do it for job, then we get the intercept term. The drivers were the reference, so then we sort of basically say, are they conductors or are they bank workers? So these ones were conductors and these ones were bank workers. These ones were conductors and these ones were bank workers, and that is the linear predictor. Eta is equal to beta naught plus beta 1 times I, are they a conductor, plus beta 2 times I, are they a bank worker? If we drop the intercept term, again, it doesn't actually make it smaller. It basically says, are they drivers or are they conductors or are they bank workers? And here's the linear predictor. Okay, then if we have a main effects model for high energy and job, and that's the formula. Again, it defaults to giving us an intercept term, and then it says, are they high energy, or are they conductors, or are they bank workers? And that's the linear predictor there. Gets a little more tricky when we start to have both a main effect and an interaction model. So we have the main effect for high energy, a main effect for job, and an interaction between high energy and job. And what I might do is I might start off with the linear predictor here, where we have that eta is equal to an intercept term plus a main effect for high energy is equal to high, plus a main effect for conductors, plus a main effect for bank workers, compared with low energy and drivers. And then we have an interaction term between for those that are both high energy and conductors, and an interaction term for those who are both high energy and bank workers. So again, we have an intercept term, main effect for high, main effect for conductors, main effect for bank workers, and then these are the ones who were both high energy diets who are conductors, and these are the ones who were both who had a high energy diet, and they were bank workers. Now, if we do a job main effect and an interaction between high energy and job, then what we can do is we get an intercept term plus a main effect for job and a main effect for job. And then we say, well, what is the interaction between they were high energy and a driver? High energy and a conductor, high energy and a bank worker. So then this has the same degrees of freedom as this equation here. It'll actually have the same model fit criteria, but the parameters are interpreted differently. We get the intercept term, get the main effect for conductors, main effect for bank workers, but then we get high energy and driver, high energy and conductor, high energy and bank worker. And this can be very nice because it basically says what is the effective high energy for each of these three groups after we adjust for main effects for job. And then what we can do is we can adjust for a main effect for high energy and then an interaction. So what we do is we get an intercept term, a main effect for high energy, and then what we do is for the conductors, what's low energy, and then for the conductors, effective high energy, and then for the bank workers, the effective low energy, and then for the bank workers, the effective high energy. To finish off with this, what we can do is we could possibly have main effects for high energy and the continuous. So what we do is we have an intercept term, a main effect for high energy, and then a main effect for x. So then we get a bunch of ones, a bunch of indicators for high energy, and then the actual values for x. And then if we were to look at, I think you can ignore this row, what we do is main effect for high energy plus an interaction. But between those, we get an intercept term, get a main effect for high energy, and a main effect for x, and then an interaction. So if we actually do the product of these pairs, then we get zeros here, and then 4, 5, and 6. So then we have intercept, main effect for high energy, main effect for x, and then a product between the effect for high and x. Right, so that was a lot to take in. What we're going to do now is we're going to use those design matrices and linear predictors to investigate the relationships in the diet data set. First thing that we do is we actually look at the numbers of events. So we use the serve rate for time on study expressed per 1,000 person years for CHD, stratified by high energy from the diet data. And what we find is that for the low energy, we have 28 events, and from the high energy, we have 18 events with slightly more person time. And this is, don't forget, this is per 1,000 person years. So this is actually 2,544 person years. And then we get rates of 13.6 in the low energy and 7.1 in the high energy, and then we get confidence intervals. And don't forget, this is the overall rates of CHD, which is not adjusted for any potential confounders. Typically, what we would do is we'd look at this 7.1 divided by the 13.6 to show the incidence rate ratio, which shows that the high energy diet had a considerably lower incidence rate ratio than the low energy diet. But we're not controlling for any possible confounding factors. And so this is sometimes called a crude estimate that is not adjusted for potential confounders. Now, it would be useful to reflect, is this a true effect, and what are the important confounders that we might need to consider? So when working with rates, the historical assumption has been that actually oftentimes it makes most sense to assume that they would tend to be multiplicative. So that means what we're basically saying is that the low energy group is likely to be a multiple of the rate for the high energy group, lambda 1, is likely to be a multiple of the rate for the low energy group, lambda 0. So it means lambda 1 is equal to lambda 0 times theta. So that means 7.1 per 1,000 is equal to 13.6 per 1,000 times 0.52, or theta is equal to lambda 1 over lambda 0. If the explanatory variable x is equal to 1 for individuals with a high energy diet and 0 for individuals with a low, then we can write lambda as a function of x is equal to the baseline times theta to the power of x. So that means if x is 1, then it's lambda 0, and if x is 0, then it's lambda 0, and if x is 1, then theta to the power of 1 is equal to theta. So then it's this. Okay. In practice, it's often more convenient to work on a logarithmic scale. So that means lambda is equal to lambda naught times theta to the x. These are inverses. Then the product becomes a sum. The product, a log of a product is equal to the sum of the logs. And don't forget that we've got log theta to the x is equal to x log theta. So then what we get is an intercept term and a main effect for x on the log scale. So beta naught is equal to log of the baseline rate, and beta 1 is equal to log of the incidence rate ratio. What's nice is that on the log scale, the effects are additive. So we've basically moved from a multiplicative scale to an additive scale using logs, which is very similar to what we do for logistic. And for an increase of 1 unit in x, the log rate increases with the constant factor of log theta, which is equal to beta 1. So this is a Poisson regression model with one explanatory variable, x. And importantly, the regression model in this case is actually based on the hazard. So as an exercise, can you do the calculation for what is beta naught and beta 1? What we find is that beta naught is equal to the log of the rate per 1000, so it's log of 13.6, and beta 1 is the log of the incidence rate ratio, so it's log of 0.52. So the formulas that we have for regression models so far, we have linear regression where the mean value is equal to an intercept term plus beta 1 times x, or if you've got logistic, then the log of the odds is equal to beta naught plus beta 1 times x, and in Poisson what we have is that the log of the rate is equal to beta naught of beta 1 times x if we've got an intercept and one explanatory variable. The interpretation of the beta 1 varies. For the first case, it's actually the change in mean for a unit increase in x. For here, it's a change in the log odds per unit increase in x, and here it's the change in the log rate for a unit increase in x. If we assume a Poisson regression model, then we have that log of 0 is equal to beta naught plus beta 1 times x. And when x is equal to 0, then we have that beta naught is equal to minus 4.3. And if x is equal to 1, then we have beta naught plus beta 1. So that means beta 1 is equal to log of these values, which is equal to minus 0.653. Conversely, if we exponentiate this, then we get back to exponential of beta 1, which is the incidence rate ratio of 0.52. Poisson regression as a model for rates. Generally, when we do Poisson regression, it's for counts. Now, if the count is y and the person time is t, and in this case, this is not a variable, this is just meant to be the observed person time, we're assuming that's fixed, then for the above, we have that the rate is equal to the expected value or observed of, well, this is assuming a modeled rate of y, which is the observed count, divided by t, which is the observed person time. and we're assuming that's equal to exponential of beta naught for the intercept term and beta 1 times x. Now, this is constant, so then what we have is that exponential, so the expected value for the count is equal to exponential of beta naught plus beta 1x times t. And then, so t is equal to exponential of log t. So then we can put it inside here. So that means the expected count is equal to beta naught plus beta 1 times x plus log t. Suddenly, if we do this, then this has got these have interpretations and as being log rate for the baseline and a log of the incidence rate ratio. So if we use log of person time as a value in here, then we move from modeling for counts to modeling for rates. What's interesting about this is that this log t, there's no beta here, and it's actually it's essentially a constant in the linear predictor, and that's termed an offset. So it's I think I might have a slide for that. So okay, we'll come back to offsets. So for the diet data, we could have used either transform or mutate. So we basically take a copy of the diet data from the package and put it into the sort of the working frame, and we calculate y, which I think is actually already available, but in this case we will recalculate y as the date of exit minus the date of entry divided by 365. So this adds a new observation y onto, so a new variable y onto diet. And I actually think we could probably ignore that line because I think y is already exists. Then we calculate a new object called fit, which is a generalized linear model, which is Poisson regression, using the data where we use CHD as the outcome, where we adjust for high energy diet, and then we do an offset, which means it's a fixed value for the log of the person time. And then what we do is this is equal to beta naught, and this is equal to beta 1. We also get the standard errors and test statistics and p-values based on the WOL test. So this is highly significant, and this is significant as well at 3%. Then what we can do is we can use a utility function from the Biostatistics III package, where we get the exponential form from this object, and this gives us the incidence rate ratios and the 95% confidence intervals for this is this is the baseline rate, and then this is the incidence rate ratio. Poisson regression is one type of generalized linear model. Two others that we know already are linear regression and logistic regression. And the model is estimated using maximum likelihood, which means that we can assume that these betas are, you can assume that beta hat is normally distributed. Confidence intervals are constructed by the assumption that the estimated regression parameters are normally distributed, and we actually do that on the log scale. So we get the beta hat, then we subtract 1.96 times the standard error, and then we take the exponential to get the lower, and then exponential of the estimated parameter plus 1.96 times the standard error for that parameter. So you see that the confidence intervals are simply the exponential limits of the betas, and that the confidence interval for the incidence rate ratio is not symmetric around the point estimate for the IRR. It'll be symmetric around the point estimates for the log IIR. Okay, so what happened to the timescale? The model that we just fitted did not take into account that the rates may actually vary over the follow-up time. And we used time since entry as the timescale, but the rate that we estimated was the overall rate of coronary heart disease throughout the follow-up. Simply all of the events of the CHD were divided by the total person time at risk. When we estimate the overall rate, we assume that the rates, in this case, are about 13.6 per thousand person years among the low energy group and 7.1 among the high energy, are assumed to be constant throughout the follow-up time. We will come back to this issue, but first what we're going to do is we're going to investigate how to model for main effects and interactions for Poisson regression. So what we have for the diet data, we've got a variable high end, which is two levels, which are high and low, and there's going to be we're going to create a variable called end3, which has got 3 levels. So what we do is we make a copy of the diet, and this comes from the Biostat 3 package, and this will be in the global frame. We transform the data frame. We could also have used mutate, and then we create a new variable called eng3, where we cut the continuous energy variable, and we do splits at 0, 1500, 2500, 3000, 4500, and this is infinity. And then we do right is equal to false, which means that we have the left-hand side is included, and then the right-hand side is not. And then what we can do is we can look at the rates by these groups for the diet data, where we take the date of exit minus the date of entry per year per 1,000 person years with CHD as the outcome. And then what we have is we get the number of events in each of these energy groups and the person time and the rates with 95% confidence interval for the rates. To include eng3 in regression functions, we can simplify this, and we could just include 0, 1, or true, false. So we could define x1 as being energy is less than 2000, x2 is between 2000 and 3000, and x3 is between 3000 and 4500. And then we can use x1 as the reference, which means that we include x2 and x3 in the linear predictor, and we include offset of log of the person time, so that these are counts, and then we are modeling for rates from the using the diet data for Poisson regression as a generalized linear model, and then we use E-form to get the incidence rate ratios. So this is the this is the rate for the baseline, and then these are the incidence ratios comparing this level with this level, and this is the rate ratio comparing this level with this level. So in terms of the parameters, what we have is that the log of the rate is equal to some intercept term plus beta 2 times the x2 indicator plus beta 3 times the x3 indicator. So level 1 in x2 and x3 will both be 0. We just have the beta naught. If it's label 2, then this will be true as well. And we have the intercept plus beta 2, and if x3 is true, then we have beta 0 plus beta 3. The baseline is by default the first level of the factor, and we can change that to say the third level if we did a re-level on N3 with the new baseline. And then these will now be compared, so these values here will now be compared with this new baseline. That value here will be compared with this new baseline. Note that the model fit for the actual model fit statistics will be the same, but the interpretation of these parameters will be different. Where now this will be the rate for the reference group, and then these will be the rate ratios compared with the reference group. So if we've got a continuous exposure like energy, and so what we can do is we can sort of say how to coronary heart disease incidence rates vary by unit change in energy. Then what we can do when we fit this model is we get a number here which is actually very, very close to 1, but because the units for energy are quite small. For each 1 unit increase in energy, the CHD rate is reduced by approximately 0.1%, and the units of energy are kilocalories per day. And we sort of see that the median and the mean values are quite high with a reasonable range. What we could do instead is say we want to get the incidence rate ratio for an increase of say 10,000 units. We use this I notation again. So it's energy divided by 1,000, and we want a variable for that for rates. And then what we find is that we get an incidence rate ratio of 0.89, and that's also can be calculated as being the 0.99885 to the power of 100. So that means for each 100 unit increase in energy intake, the CHD rate is reduced by about 11%. If the true exposure, the true effect of exposure does not vary across strata of another variable, then we can use a main effects model. As an example, if high energy differs only randomly over age, we can consider a model in which the true effect is constant over age. So that's that would be equivalent to saying there is no interaction. So this allows us to combine the information from the different strata to yield a single estimate of the exposure effect. This combined estimate of the effect we call the main effect, which is then controlled for the stratifying or confounding variables. Statistical tests for the presence of effect modification are available, although there are no formal statistical tests for confounding, and that should be done on the basis of subject matter knowledge. To show what we do here is we're going to do an adjustment for high energy, which is in 2 groups, and job, which is in 3 groups. So we expect to have 2 minus 1 covariates for high energy, and 3 minus 1 coefficients for job. What we find is that high energy high compared with low, job conductor compared with drivers, and job bank compared with drivers. And what we find here is that after adjusting for job, that the effective high energy is still close to a half, and that is statistically significant. Conversely, after adjusting for high energy diet. Conductors are not different to drivers, and bank workers are not different to drivers because the confidence intervals both overlap 1. So what we have is that because we still assume that the rates are constant over time, that the rates are assumed to be a function of both high energy and job. So that means this rate is equal to exponential of the intercept term plus the main effect for high plus the main effect for conductors plus the main effect for bank workers. The estimated incidence rate ratio for high energy diet versus a low energy diet, so we're comparing high with low for any given job, is equal to this from the previous page divided by this. And the nice thing here is that the beta naughts cancel out, beta 2 cancels out, beta 3 cancels out, that all cancels out, and we're just left with exponential of beta 1. And the very nice property here is that this is independent of job. So the incidence rate ratio comparing a conductor to a driver for a given high or low energy diet, comparing conductors with drivers, then what we find here is that cancels out, and we're left with exponential of beta 2, which again is independent of whether they have a high or low energy diet. And part of the reason why we like the main effects is that they have a very broad interpretation for adjustment given other factors. However, they also do assume that those effects do not change across those other factors. So what we can do, instead of looking at the incidence rate ratios, we could also look at this in terms of the coefficients themselves. So adjusting for high energy and job, and we find that this is the log rate for the baseline group. That's the log incidence rate ratio for high energy compared with low, log incidence rate ratio for drivers compared with conductors, and log incidence rate ratio for bank workers compared with drivers. Again, that's significant and that's significant, but these effects are not. However, if the true effect of exposure does vary across strata of another variable, there is said to be effect modification. The effect of exposure cannot then be represented by one incidence rate ratio. So the research question we have is, does job modify the effect of high energy? If we estimate the incidence rate ratio of high energy separately in all 3 groups, we basically split the data set into 3 groups, do the analysis for each of those groups. Then what we find is that the effective energy for drivers is 0.41, conductors is 0.66, and bank workers is 0.52. And the question we have is, are those estimates different? Then what we can do is we fit a main effect for high energy, a main effect for job, and we fit an interaction between those. That's the main effect for high energy. These are the main effects for job, and then these are the interaction effects for high energy for conductors and high energy for bank workers. The interpretation here is that we have a regression model where we have an intercept, main effects, and 2 interaction terms. And if we want to estimate an incidence rate ratio for high energy diet versus a low energy diet for a given job, then this is now we have that the intercept terms cancel out. That beta 2 times here cancels out with that. Beta 3 times here cancels out with that, but we still have these terms here. So what we have is that the incidence rate ratio for a high energy diet is exponential of this value here for the drivers, plus an additional component if they're a conductor, or an additional component if they're a bank worker. So if they're a driver, it's just this. If they're a conductor, then it's this, and if they're a bank worker, then it's beta 1 plus beta 5. And what we see is that the incidence rate ratio will be dependent on the type of job unless both beta 4 and beta 5 are equal to 0. So the estimated incidence rate ratio comparing a conductor to a driver for a given type of diet is equal to this divided by this. What we find is that this cancels out and that cancels out. So then what we find is if they're on a low energy diet, that is the effect for comparing a conductor with a driver. And if they're on a high energy diet, it'll be this plus this. And again, this is dependent on whether they have a low or a high energy diet, unless beta 4s equal to 0. So to test whether the interactions are significant, we need to know if the interaction parameters are equal to 0 or not. For the model that we fitted, what we can do is we can do an ANOVA test on the fit, and then we find that, well, first of all, there's no strong effect for job, but also there is no significant effect for high energy and job with 2 degrees of freedom. So the null hypothesis here is that the betas, that the interaction terms, the 2 interaction terms, are equal to 0. There's very, very weak support for there's very strong support for the null hypothesis. So there's no evidence of a statistically significant interaction. And this is called a Wald test, which approximates the likelihood ratio test. Could also have done a likelihood ratio test by fitting the 2 models and comparing them. So there's a shorthand here. If we've got 2 main effects and an interaction, an equivalent formula would be to do A times B. So A times B expands out to being this. If we had A plus B plus C raised to the power of 2 minus AC, then basically we get the main effects for A, B, and C. We get all the two-way interactions between those, because this is squared, and then we take out the AC. So that's the main effects, AB and BC, but we excluded the interaction between A and C. And then if you've got A less the intercept, that's actually equivalent to be A plus 0. We have already introduced the I term, where you can use mathematical operators in the formula if you use this wrapper. And as a reminder, the log x will lead to a parameter being estimated for the term, while if you use an offset term, it will treat the value as a constant and does not estimate a parameter. We may be interested in the effect of an exposure for each level of the modifier. And so what we could do is we could re-parameterize the model to directly estimate parameters of interest. So far as we might want to look at, might want to use the same model to estimate what is the effect of high energy for drivers, for conductors, and for bank workers. There's several ways we could do that. So we've already done this, and what we've said. Oh no, this is re-parameterized. So what we could do is say we want to have an intercept term, and then main effects for job, and then we want to have interactions between driver and high energy, conductor and high energy, and bank worker and high energy. And importantly here, we've dropped the main effect for high energy. So now we have 3 interaction terms rather than 2. So, and then the estimated incidence rate ratio for high energy diet versus a low energy diet for a given job is equal to this value at the top divided by this value down the bottom, and then again very nicely we find that the beta 1, beta 0, and the beta 2 all cancels out there, and then we have a value here for drivers, a value here for conductors, and a value here for bank workers, and which will be dependent on the type of job, unless beta 3, beta 4, and beta 5 are all the same. Instead of just one baseline rate, we now need 3, and so what we do is we do an E-form on this. We main effect for job, and then an interaction here. You get the main effects for job here, and then you get the 3 interaction effects. And then these values here, here, and here look very, very similar to what we got when we actually estimated the stratified effects, which is not surprising. Note that this is the same model. There are still 6 parameters, and the fitted values are identical. It's just that the 6 parameters now have a different interpretation. If we insert the R into our previous output, we again pull out and that the stratum specific incidence rate ratios are similar, and that there is no evidence of an interaction. What we can also do is we can take a fit which has been parameterized one way and then use linear combinations of the parameters to estimate other contrasts. So if we start out doing a main effects and interaction, so main effect for high energy, main effect for job, and an interaction between high energy and job, it's main effects, and then we get the 2 here. For that model, which is called fit, we can now do a linear combination from the fit for high energy plus the interaction, which gives us the 0.66, and then high energy and job workers, which gives us the 0.52. And then the E-form says that we want this to be exponentiated. So this says that we can actually fit one model and then express a linear combination of the parameters, which is what we'd got if we dropped off the main effect for high energy, which is really quite beautiful. Now the calculation for the point estimates would be straightforward. It'd just be the 0.41 times the 1.56, which is gives us 0.6. That isn't difficult. What's more tricky is actually getting the confidence intervals and the test statistics right. And then the lincom command from the Biostat 3 package can be very, very useful. We now come back to thinking about time varying rates. So far, we have modeled the overall rate, such that we've assumed a constant rate throughout follow-up, and we've also modeled how the overall rate can vary according to other variables, and we've thought about main effects models, and we've also thought about including interactions. Now what we'd like to do is see how can we model and adjust for time when it confounds for the effect of interest? And the elegant way that we can model time is one of the beauties of survival analysis. First of all, we'll look at using time as a confounder, and then we'll also look at time as being an effect modifier. Okay, for which calendar period is mortality lowest? And so what we find initially, we'll look at survival using Kaplan-Meier, and it looks like the slope here is quite steep, and then the slope decreases here. So the survival is changing comparatively slowly here and here, but it's much faster here. And then if we do a kernel smoothed hazard, what we find is that the hazards are quite high here and then much lower here. So that means where the follow-up is will actually affect the modeling of the rates. And in particular, this is our overall rate would be assuming that this is constant, and which and there's very strong evidence from this that it is not constant. As a review of what we discussed before, do broadly interpret the kernel smooth hazards, but don't overinterpret some of the small patterns here, as they could be artifacts of the choice of the bandwidth. So for which calendar period is mortality lowest? So what we have is that if we do the this is date of exit minus the date of diagnosis per 1,000 because specific mortality from the colon data for localized cancer. And this is again assuming that it's constant, where we get 905 events for those diagnosed in the first, earlier calendar period, and 829 events for the later. We have more person time follow-up in the earlier compared with the later. So this suggests, and the rates are 44 here and 54 here. This suggests that patients diagnosed in the more recent calendar period have, so the graphs suggest that survival is better in the more recent calendar period, while this suggests that the more recent calendar period has got a higher rate. Oh, if I turn it off. So what we have here is that this rate here is actually higher than this rate here, which is inconsistent with the survival curves. Those diagnosed in the later calendar period have got less follow-up, and since the effect is highest in the early years of follow-up, the rates are confounded by follow-up time. When the rates change with time, then the time may confound the effects of exposure. We will, for the moment, assume that the rates are constant within broad time bands, but can change from band to band. This approach, where we basically take a continuous variable and put it into chunks, is fairly common in epidemiology. And we often categorize metric variables. The only difference here is that the variable is time. So we do bins between 0 and 5, 5 and 10, and 10 and 15. And then what we do is we see that you've got person time here and an event. And you have person time here and person time here for the first interval. So, and then what we find here is that there are no events in this time interval, but we have person time here and person time here, And then for this interval here, we have person time here and one event. What are the estimated failure rates, lambda 1, lambda 2, and lambda 3 for each of these time bands? Then beautifully, what we can do is we can collapse across. So then we have 13 person years and one event. We have 0 events and 9 person years. We have 1 event and 2 person years. A convenient way to fit these models using a computer is to replace the single record for each subject by up to 3 new records, one for each of the time bands. So the first subject has just the one time band. They were in 0 to 5. They had 3 person years and one failure. Second subject gave 5 person years to the first interval, 4 person years to the second interval, and no events. The third subject, 5 person years for the first interval, 5 for the second, 2 for the third, and 1 event at the end. So before you actually do split data, it's really quite useful to check the data before and after splitting. So what we do, we've got the diet data, we transform it again to calculate survival as being date of exit minus date of entry divided by 365.24 for CHD events. And then we show from the diet data the ID 35. And so we have serve, which is here. So they have 7.7 person years, and there was an event at the end, which is consistent with this here. And then we do the diet 2, where we split the diet data for date of exit minus date of entry, and then we cut in 2-year bands, and we call the episode's time band. And then now, if we actually do a subset on time band for the same individual, and we want to show their ID, time start, time stop, CHD indicator, and time band, then what we have is ID 34 goes from 0 to 2 with no event, 2 to 4 with no event, 4 to 6 with no event, 6 to 7.71 with one event, and these are just numbers for each of the time bands. Then what we can do is, once we've split the data, we can then recombine the data to look at the rates and how they change by time band. So this says that there were 6 events in the first 2 years, then 3, 11, 8, and so forth. Then we can also get the rates, the person time, and then we can calculate the rates. So it's 0.009, 0.005. It's much higher here and quite high here. And but then what we find is that the numbers can be quite small. Don't forget, a 0 event still has person time associated, so they don't drop out, and that they don't cause any problems so far as the GLMs, because a count of 0 is still a 0, and the person time is important. Then what we can do is we can now do an adjustment here for a GLM, adjusting for high energy for the person time exposed on an individual level, and then we can get a log incidence rate ratio or a rate ratio using the eForm function. However, this does not adjust for time. To adjust for time, what we can do As an example, is we can include a factor here. This does start to cause some problems because there were no events in some of these time intervals, which is the reason that we get these strange results here. But what this does is it says that we're doing a main effect for time, adjusting for high energy. Conversely, what is high energy after adjusting for time band? And strangely enough, that really doesn't change very much at all. So after adjusting for time band in these fairly small bands, we still find that the effect of high energy diet is not confounded with time. We could also use time band or the interval midpoint as a linear effect. So instead of doing a factor, we calculate the midpoint of t start, t stop, and t start, and then this would be linear. So after adjusting for a linear effective time, which is decreasing, we still find much the same incidence rate ratio. More elegantly, we could also model for the time midpoints using splines or some other smooth function, and then we wouldn't lose the time bands with zero events. And that's actually a really it's a very nice approach. There is no reason to believe that time on study would be a confounder for these data. This would, however, be of interest in the cancer examples. And the reason that this that we don't believe this is that when we did the rate patterns by time on study, the rates were fairly flat. So we could also split the follow-up on the age scale. And so what we do is we do surf split for the diet data, creating something called age band, which would be 10-year age groups going between 40 and 70. So those are the cuts. And then we have, these are the age at entry, age at exit, and the CHD. And the dot here says include all of the variables. And then if we do a subset for ID 34 again for the same variables, except that we now include age band, that we have that this individual entered at age 59.84, followed through to 60 with no event, and then followed from 60 to 67, and then at the end they had their event, and this was age band 3 and age band 4. And then we can adjust for age band here, and this is treating it as being a factor. And then what we have is we've got 0, 6, 18, 22, and 0. So that means this person time will fall out, and this person time will fall out if we model the age bands as being a factor. While if we actually did a smoother on this of some sort, they would stay in, but there's very few here. So, oh, sorry. And we can also see that the incidence rates rise with age, except for the last group, which is 0. So to adjust for attained age, we do factor here. As we saw from here, it will treat this as being the reference and compare with these two groups. And then we find that this changes marginally. It goes from 0.52 to 0.54 after adjusting for attained age. So is there evidence of the effect of high energy being confounded by attained age? It's changing less than 10% and not much really. Fine time splitting on one or more of the time scales can actually make the data set very large. Usually for time segments with other covariates, we can also collapse, and this is important, where we can sum the events and sum the person time. So if we have the split two data, which was split by age band and high energy, then we group here, and then we sum up the CHD, sum up the person time. And then this we now only have 6 observations. That's it. And then from that, what we can do is from the 3 data, we can model this, and then what we find is we get identical estimates here to what we had previously. So we've collapsed by the events and the person time for the variables included, and we get the same fit. Usefully, we can also split by multiple timescales. This is where things get quite exciting. So if you first split by attained age, and then what we do is we take the year of birth here, and then we're going to use the year of birth here for year of birth plus t start and year of birth plus t stop to get attained year. So, and then we basically end up having variables for age band and year, and then we do factor age band and factor year here. And the summary from that shows that year is significant. The third age group, age band 3, is significant, but this is not. So this means that we can adjust for both attained age and attained year, or you could do attained age and time on study. Now sort of take a bit of a sort of like a step back and think about when and why we want to use statistical models. And the regression models that we've described, that they are important because they allow for simultaneous estimation and testing of the effect of many prognostic factors on survival. And the aim of that the modeling is to derive a mathematical relationship of those relationships together with a measure of the uncertainty. And broadly speaking, statistical models can be used in 3 areas. First is the descriptive, where we simply just want to describe broad patterns, and this is often used for hypothesis generating. Then we might want to do hypothesis testing, where we actually want to just statistically test whether an observed response variable is associated with one or more explanatory variables, and this is often closely aligned with etiology or causal inference. And then the third is prediction, where we want to actually sort of be able to predict excess mortality for a future time period, or predict the way in which the outcome may change if certain explanatory variables were changed. Note, and this is an you've probably heard this before, but that we can never assume that a statistical model is true, but the models may be useful. When making inference based on the model, we do then assume that the model is true. So then the interpretation of the model parameters should be, in some sense, modulated by whether we think that the model is close to being true. If the model is poorly specified, then the inference will be erroneous. It's therefore important to consider the validity of any assumptions such as proportional hazards underlying the model, and to check for evidence of lack of fit. Okay, to summarize, a rate can be calculated from the events divided by the total time at risk, where time at risk is usually measured in person years or person months. that rates can vary across various timescales, such as time since entry, attained age, and calendar period. We can model the rates using Poisson regression, which estimates the baseline rate and the incidence ratios for different exposure levels. We've talked about re-parameterization of interactions. We've also talked about that rates and incidence rate ratios can be confounded by time. And actually, this is wrong. I took this out. What you can do is you can use the collapse data, which we have discussed, to assess goodness of fit, but I have removed that material. So exercises for Wednesday. The key exercise here is exercise 7, which is looking at cause specific mortality for localized melanoma, and then this will be compared to exercise 9 on Friday. And then we can also talk about tabulations, and then if you've got time, looking at Poisson regression to study the effect of energy intake adjusted for confounders. And that's the one reference. Thank you very much.